In this lecture, we are going to discuss about the numericals and electrical machines to part 3. A delta connected 6-pole 50 Hz three-phase induction motor has a rotor resistance of 0.15 ohm per phase, exerts a maximum torque at a 880 rpm. Calculate the percentage maximum torque that would exerted at a standstill condition. Second one is at 940 rpm. Now, first you are going to find the synchronous speed. Synchronous speed is equal to 120 FFP. Substitute all the values, you are getting the 1000 RPM. The speed of a motor at the maximum torque that is given in the numerical, that is 880 RPM. So the slip corresponding to the maximum torque Sn equal to Ns minus N by Ns. You are getting the 1000 minus 880 RPM by 1000, you are getting the 0.12. We know the formula for the starting torque to the maximum torque, that is equal to 2 Sm by 1 plus Sm square. Substitute all the values, we are getting the 0. Now the starting torque equal to 23.66% of the maximum torque of an induction motor. Now you have to find out the what is the ratio between the full load torque to the maximum torque. See, 940 RPM you have taken as a full load speed of a motor. The suppose induction motor at a full load equal to Ns minus N by Ns, you are getting the 0.06. So T full load by T maximum equal to 2 Sm SFL by Sm square plus SFL square. Substitute all the values, you are getting the 0.8. So the full load torque equal to 80% of the maximum. Now come to the second numerical. A three-phase 50 Hz induction motor has a starting torque which is equal to 1.2 times the full load torque and maximum torque is 2.5 times the full load torque. Neglecting the stator resistance and rotor losses, calculate the slip at a full load. T starting equal to 1.25 times the full load. T maximum equal to 2.5 times the full load torque. This is given in the numerical. Now take the ratio between the equation 1 to the 2. We are getting the T starting by T maximum equal to 2 Sm by 1 plus Sm square. We know this one. So when you take the ratio between 1 by 2, on the right hand side, we are getting 1.25 by 2.5. We are getting a 0.5. So Sm square minus 4 Sm plus 1 equal to 0. If you find the roots of this equation, we are getting a 0.268. This is the slip corresponding to the maximum torque of the induction motor. Next, T full load by T maximum. We know the formula for the T full load by T maximum, that is equal to 2 Sm SFL by Sm square plus SFL square. We should know this quantity. So now you take the equation 2. Now you find the ratio between the T full load by T maximum. Then you will get 1 by 2.5 on the left hand side of this equation. Substitute the remaining all the values. Solve this equation, then you are getting the one more quadratic equation in terms of a slip at a full load. SFL square minus 1.334 SFL plus 0.0718. If we solve this one, we are getting the slip at a full load equal to 0.05. So the slip at a full load equal to 5.6%. Slip at a maximum torque, already we talked about this one, this is equal to 26.8%. Now I have to find out the rotor current that is starting I2 equal to E2 by square root of R2 square plus X2 square. The rotor current in the running condition IR equal to SE2 by square root of R2 square plus SX2 whole square. In the denominator, you take the common S. So finally, you are getting the E2 by square root of R2 by S whole square plus X2 square. Now we take the ratio between these two and simplify the expression. We are getting the square root of R2 by S whole square plus X2 square divided by square root of R2 square plus X2 square. So here we have taken the X2 common in both numerator and denominator. So square root of R2 by X2 by S whole square plus 1 divided by square root of R2 by X2 whole square plus 1. You know this one, this is the slip corresponding to the maximum torque. Substitute all the values, we are getting the 4.722. Nothing but the starting current equal to 4.722 of rotor current in a running condition. So third numerical. Induction motor runs at a slip frequency of 2 Hz when supplied from the three-phase 400 volt 50 Hz supply for same developed torque, the slip frequency at which it will run when supplied from the three-phase 340 volt 40 Hz system. The slip at which the machine develops a maximum torque using a 50 Hz supply is 0.1. Neglecting the stator impedance, assume the linear slip torque characteristics between 0 to the maximum torque development induction. At a 400 volts, 50 Hz, the slip of the induction motor that you want to take it is S1, that is equal to Fr dash by Fr, we are getting the 2 by 50. This is given in a numerical, this is 2 hits is given. So 0.04. So ratio of rotor resistance to standstill reactance R2 by X2 equal to Sm, that is equal to 0.1. It is also given in the numerical. So R2 equal to 0.1 X2. The torque developed at a slip of S1 equal to 0.04. This is the general expression for the torque developed in induction motor. Substitute all the values. In place of R2, you substitute the 0.1 X2 and simplify this expression. We are getting the 6400 K divided by 0.0116 X2 square, where K is nothing but a motor cost. At 300 volts 40 Hz supply, where the machine develops a torque equal to T1 at a slip of S2. Suppose the same machine is exerted with a 300 volts and 40 Hz, then the developed torque K into S2 into 440 here by 0.1 X2 plus X2 into S2 equal to the developed torque in an induction motor in the first case, that is 6400 K by 0.0116 X2 square. K gets cancelled. If you simplify this one, finally we are getting the X2 square 0.2095 S2 plus 0.01 equal to 0. Again, we are getting the quadratic equation. If you find the roots of this quadratic equation, we are getting the 0.07356 and 0.1359. Higher value rejecting. So the slip of the induction motor S equal to 0.07356. So the slip frequency in second case, F1 dash equal to S2 into F. So we are getting the 0.07356 into 40. We are getting the 2.94 Hz. This is the slip frequency of induction motor when it is exerted with a 300 volts and 40 Hz supply. Thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am always welcome to answer you.